Hello, it's Anya. In this video, we are going to talk about E, which is also known as Euler's number. If you're math enthusiasts and avid watchers of science channels like us, you are probably, at least to some extent, familiar with this subject. However, we are not going to focus on the basic stuff, but we'll go a little further and explain why the same mathematical constant appears in several seemingly unrelated formulas. There are many ways of defining E. We chose 5, each connected to a different central object in mathematical analysis. So we have E expressed in terms of limits, series, derivatives, integrals, and local extrema. Of course, there are precise arguments showing that each of these definitions leads to the same number. But as our goal here is to have some fun with maths, we will try to connect the dots in a less conventional way. We fully rely on the following 6th definition, which is slightly less strict. It is, however, important historically, since this is the approach to which E owes all the attention it gets. We'll start with a quick financial mathematics warm-up. Imagine you put $1 into your account and the bank gives you 100% interest each year. How much money will you have after a year? It's easy, like 1 + 1 is 2. Now let's make it more complicated. What if your account compounds interest twice a year? Your dollar earns $0.50 after 6 months and another $0.50 after the next 6 months. But that's not all. The first $0.50 earns as well $0.25 for the last 6 months. Together, we have $2.25, which equivalently can be written as 1 + a half squared. The latter formula is easy to explain, as every half a year your amount of money is multiplied by 1 + a half. In case of 3 compounding periods, lasting 4 months each, the situation looks similar. And the final result is this or this. What we are dealing with here is called the compound interest formula. For an annual interest rate of 100% and n equal compounding periods every year, it will take the form 1 + 1/n to the power of n. You can check by yourself that the bigger n is, the greater amount of money you get. Now, if we imagine that the continuous compounding corresponds to letting n to infinity, we obtain the following formula for E. Okay, that was clever, but probably some of you have heard about this before. Now let's move on to something slightly less commonly known. Do you remember what changed when the number of compounding periods increased? Apart from the amount of money that you had from the beginning, interest, interest on interest, and so on, started to appear on your account. Let's focus on the case of continuous compounding and divide your money into groups according to its origin. So in the group number 0, put your initial dollar. In the group number 1, put the money earned as interest on your base amount, and so on. Namely, in the group number n+1, put the money earned as interest on the money collected in the group number n. As we are in the continuous case, there are in fact infinitely many such groups. Denote by Sn of t the amount of money in the nth group after time t. Then, for a given moment t, the speed of growth of money in the group number n+1 is proportional to the amount of money in the group number n. Moreover, by our assumption of 100% interest rate, the proportionality constant equals 1. Our goal is to compute the total amount of money after a year, which is S0 of 1 plus S1 of 1 plus S2 of 1 plus etc. Before that, let's learn how to calculate Sn of t for each particular n and t, starting from the easiest case. Of course, S0 of t constantly equals 1, as it represents the initial dollar. S1 of t, in turn, equals t, as in this case, the amount of money increases linearly, giving $1 after a year. For larger values of n, we can proceed inductively using the Newton-Leibniz formula and the proportionality rule described above. In each step, we use the values computed previously. Thus, a memory box like this will be helpful. For n equal to 2, we get the following expression, which gives S2 of 1 equal to 1/2. Similarly, for n equal to 3, we get this. And for general n, this. Putting all together, we obtain another known formula for E. Let's move on to the definition of E in terms of the derivative. Here, the exponential functions of the following form appear. The use of the letter t is not accidental, as this class of functions is good at describing certain processes occurring in time. For example, population growth, radioactive decay, or in our case, the compound interest rule. Indeed, assume that the method of calculating interest is independent of time and the amount of money. We have constant interest rate of beta% and continuous compounding. Suppose that after a year we derive $8 from $1, where A is a certain constant depending on beta. Then from $8 we should derive A squared, and from A squared, A cubed. Listing these observations one after another, we see that after 2 years, from $1 we derive A squared, after 3, A cubed, and so on. The amount of money in the moment t is therefore described by the exponential function a to the power of t, where a represents the amount of money possessed after a year. So what about the derivative? If in the moment t we have a to the power of t money, then the speed of growth is proportional to this quantity, and the proportionality constant equals beta%. And for which a does the equality with constant 1 occur? Of course, it happens precisely when beta is equal to 100. But in this case, we know that after a year, we are going to have E money, so E is the constant we are looking for. In other words, it is equal to the constant A associated to beta 100. For the integral definition of E, the reasoning looks like this. Let f be given by the following formula. Now, our task is to find an argument S0 such that f of S0 equals 1. Of course, this is easy for those of you who know what the natural logarithm function is and that its derivative is precisely 1 over x. Our approach focuses on finding the solution without this knowledge. Instead, we will show that f of s is equal to t of s, the function describing how much time is needed to reach the amount of s on the bank account. Consider s equal to 1. Then t of 1 equals 0, because $1 is the amount of money we have at the start. Also, f of 1 is 0 as we integrate over an interval of 0 length. So it remains to show that f prime of s equals t prime of s for all s greater than 1. Firstly, since integrating and finding derivatives as operations are opposite to each other, we deduce that the derivative of f should be the function 1 over x evaluated at s. That is 1 over s. Regarding the function t, the speed of growth of our amount of money is proportional to this amount with the proportionality constant 1. In other words, we can say that the growth of time we wait for the money is inversely proportional to the amount we have. Again, with the constant one. Informally, we have just used the formula for the derivative of the inverse function. And this was exactly what we were looking for. Now, since we know that t of e is equal to 1, we see that e is our desired argument as 0. Finally, we want to show the following inequality for each x greater than 1. Substituting x with e to the power of s, we have this, or simply this, to prove for each s greater than 0. The quantity on the left describes the ratio between f, our amount of money, and g, the time we need to wait to reach it. We shall show that this ratio is the least favorable for s equal to 1, proving the inequality we focus on. Our idea is to study the relative speed of growth, that is, the ratio between the derivative of a function and the function itself. We make calculations separately for f and g. As the following formula shows, if the relative speed of growth is greater for f, then the ratio f over g should increase with s. Otherwise, the ratio should decrease as s increases. Let us look at f and calculate the ratio between f prime and f. Of course, we already know that this ratio equals 1 for each s. For g, the situation is different. Here, the relative speed of growth is 1 over s. Thus, the relative speed of growth is greater for g if s is smaller than 1, and greater for f if s is bigger than 1. Hence, the quantity we study is indeed the smallest for s equal to 1. This is all we have prepared for you today. We hope that this presentation inspired you to think about the number e in a more diverse or creative way. Of course, there is a variety of formulas defining e that we haven't even started to discuss. So our story ends here, but many fascinating properties are still waiting to be discovered.